Okay, so second exercise of Fourier transform. So here we have the function f of theta. So it is equal to cosine of theta if x is between minus pi and pi, and otherwise the function value is 0. So the first question, we need to demonstrate that f of theta is inside the space L1 of the real numbers. So that's basically using the definition of belonging to L1. So if a function g belongs to L1, it means that if you integrate the function inside the, the real numbers, it will give us a value that do not diverge. It is less than plus infinite. So that's the definition. So if we want to demonstrate it, we're gonna simply substitute g by the function that we have, so f of theta. We are gonna integrate and then see if it is less than plus infinite. Okay, so if we integrating on the real numbers is basically integrating from minus infinite to plus infinite. Here we have our function f of theta. So since the function values 0 outside the interval of minus pi, that means that this integral that I've written here, it is equal to this integral here. And inside this interval, our function values cosine of theta. Okay, so cosine is a pair function, and we are integrating in a symmetric interval, so we can multiply by 2 and cut the interval in half. So we'll have 2 times integration between 0 and pi of cosine of theta. And now we just do the integration. So integrating cosine of theta, we'll have sine of theta going from 0 to pi. And we can see that this is 0 since sine of pi and sine of 0 values 0. So that's 2 times 0, that's equal to 0. And this is less than infinite. So we've demonstrated that our function is inside L1. Okay, so we've done the question 1. Now the second question is we need to show that the transformation, the Fourier transform of the function f of theta is equal to this, and also the function already transformed on those 2 points here, minus 1 divided by 2 pi and 1 divided by 2 pi. The function there values pi. So, okay. So here, we're gonna do the Fourier transform. And why we can do it? Since f of theta belongs to L1, now we can do the transformation. Okay, so for all values of x belonging to the real numbers, we have that the transformation of Fourier will be, so now we're just gonna write down the formula. So integral between minus infinite and plus infinite, so in the real numbers, of the function f theta times the exponential of minus 2 pi I x theta d theta. Okay, so here once gonna do that step of just changing the interval to minus pi pi, since the function value is 0 outside of this interval. And right now, once we are in the interval minus pi pi, the function f theta, it values cosine of theta. All right, and now we can do this integration by different methods. We can open cosine of theta in exponential, since cosine of theta, it is equal to, oh, sorry, the exponential, we can open it into cosine and sine, since the exponential of I times theta, it is equal to cosine of theta plus I times sine of theta. So this will give us two integrals, and I don't know how much you know about uh, trigonometric integration, but if you're good at it, it might be faster for you to solve. If you don't have anything known by heart about trigonometric integration, maybe the best solution is the one that I'm doing. So I'm gonna do integration by parts 2 times. So here we have cosine of theta and exponential. So if we integrate by parts once, this cosine of theta will become a sine of theta. So we'll have an integral of sine times the same exponential. And if we do the integration by parts one more time, this sine will turn again into a cosine of theta, and the exponential will be there as well. So if we integrate by parts 2 times, you'll reach the same integral, and then we'll have an equation, and we can solve it for the value of the integral. So it will be more clear when I do it. All right, so let's do integration by parts. Just a quick reminder, integration by parts, that's basically what we'll have. U dv equals u of v minus the integral of v du. So here we'll have cosine of theta as our u, and the dv will be the exponential times d theta. All right, so here we have uv, so cosine of theta times the integration of this exponential, that's basically the same exponential, divided by the coefficient of theta. Here we are considering x as a constant. So that's it, from minus pi to pi, minus the integral. So here we have minus pi to pi. We have v, so let's write down v is the exponential. Here we are dividing it by minus 2 pi ix. So these are constant terms. I'm gonna take it off of the integral. So 1 divided by 2 pi ix. And it is negative, so it will cut out with this negative here. So I'll put a positive sign. Okay. And now we need to multiply it by du. So we're gonna derivate cosine theta. That's minus sine of theta. Okay, so we'll have sine of theta here. And it is minus, so the positive becomes a minus. So that's it. Let's continue it. So we'll have cosine of pi, that's minus 1. So it will cut out with this minus here. So 1 divided by 2 pi ix, and exponential of minus 2 pi ix theta. And since theta is pi, we'll have minus 2 pi squared ix. And the second term, we have a minus. And then we have minus pi, so minus pi, we'll have cosine of minus pi, that's minus 1 again. And then we are going to cut out once again with this minus here on the denominator. So we'll have simply the exponential of here minus pi, so to, the power here will be positive. 2 pi squared ix divided by 2 pi ix. Okay, so we've worked with this. Now we need to write down this second integration by parts. So minus 1 divided by 2 pi ix. And now let's do the second integration by parts. So here our u will be sine of theta, and once again our dv will be the exponential. So we will have uv, so sine of theta times the integration of the exponential. And here minus and the integration between minus pi and pi. So here we already have the exponential integrated. So let's put it right here. Here we are going to divide it by minus 2 pi ix, so it will cut out and become a positive. And now we need to derivate sine of theta. That's simply cosine of theta. So cosine of theta. Okay. Now let's simplify it. So here we have the same denominator. So let's put it together. So 2 pi ix and exponential of minus 2 pi squared ix minus exponential of 2 pi squared ix minus 1 divided by 2 pi ix times. Here we are going to substitute pi and minus pi. Since we have sine of theta, sine of pi equals 0, sine of minus pi equals 0 as well. So all this term here is 0. So we won't consider it. So let's just analyze this part. So here we have minus with positive, so that's minus. But here we'll multiply the denominator, and since we will have I squared, that's minus 1. So this negative here will become a positive. So we'll have plus, and then the denominator will be 2 squared, 4, pi squared, I squared. I squared we already considered on the sign, and then x squared. And then we'll have the integral from minus pi to pi of cosine of theta exponential of minus 2 pi ix theta d theta. So if we look into it, that's exactly the integral that we were trying to integrate at the beginning. So now we have an equation and we can isolate the integral and reach to its final value. So let's rewrite the equation. So actually, this integral here is basically our Fourier transform of the function. Okay, so in order to be quickly to rewrite it, I'll just write it as this. Okay, so this that I've written here, that's equal to our Fourier transform. So reorganizing the terms here, I'll have the same exponential divided by 2 pi ix. That's equal to our transform of Fourier times 1 minus 1 divided by 4 pi squared x squared. I just moved this term here to the right as negative. So if we do this calculation here, just to simplify, we'll have 4 pi squared x squared minus 1 divided by 4 pi squared x squared. Okay, and then we can move it to the other side to in order to isolate our Fourier transform. So we'll have that our Fourier transform is equal to 4 pi squared x squared divided by 4 pi x squared minus 1. So this times this divided by 2 pi x. Okay, so we've isolated it. Now we can simplify a little bit. This 2 pi x can cut out with this numerator here. So we'll cut out the 2 pi x. And here we'll divide by 2 pi x. So this square vanishes. This square vanishes as well. And this 4 becomes a 2. All right. So now what we can do is we can transform those exponentials here into sums of sines and cosines. Okay, so let's do it. So for our transform of Fourier, we'll have 2 pi x divided by 2 pi squared x squared minus 1 times I. And now let's work with the exponentials. So just a quick reminder, exponential of I theta equals cosine of theta plus I times sine of theta. Okay, so let's do it. Here, for the first exponential, it will be cosine of minus 2 pi squared x plus I times sine of minus 2 pi squared x. And for the second exponential, let's pay attention on the negative sign. So it will be minus cosine and minus sine. So minus cosine. And here we have 2 pi squared x times I, so cosine of 2 pi squared x, and minus I sine of 2 pi squared x. Okay, so now let's analyze this. Here we have cosine of minus 2 pi squared x, so let's say cosine of minus alpha. And here we have minus cosine of alpha. Okay, we can see that this will cut out with this since we have a negative here, because cosine is a pair function. So basically cosine of alpha is equal to cosine of minus alpha. And if we are subtracting them, that's 0. Okay, so basically this will cut out with this. And then if we analyze this and this, let's analyze this one first. Okay, so we have minus 1 minus I times sine. Let's suppose that 2 pi squared x is now our alpha. So minus I times sine of alpha. Here we have I times sine of minus alpha. So if you analyze it, you can see that this one is minus what we have here, because this negative becomes a positive. And we're substituting the inverted value of what's inside here. So minus alpha instead of alpha. That's basically the definition of the odd function. So f of x is equal to minus f of minus x. So basically we'll have 2 times any one of these since they are the same. So this term here is equal to this term here. because sine is odd. So here we have the definition of the an odd function. So we can choose the one that we want to multiply by 2. It's mathematically the same, but I'll choose this one. Okay, so here we'll have the transform of Fourier of a function is equal to 2 pi x divided by 4 pi squared x squared minus 1 times I. And here our cosines vanished. And since this term is equal to this term, I'll just pick this one and multiply it by 2. So we'll have minus 2 I sine of 2 pi squared x. Okay, so this I here we'll cut out with this I here. And let's pick this negative sign and just invert the sign here on the denominator. Okay, so here we have that the transform of Fourier of our function is equal to 2 pi x. Actually, this 2 here will multiply the 2 pi x, it will become 4 pi x. Here we have sine of 2 pi squared x, and we're going to divide it by 1 minus 4 pi squared x squared, since we've inverted the sign with this minus here. Okay, so that's our final answer. We can see that it is equal to what the question told us. So 4 pi x, the sine of 2 pi squared x, and here we have 1 minus 4 pi squared x squared. Okay, so you can see that we haven't finished the question 2 because we found the transformation of Fourier. But here we have this. So we need to show that the value of our transformed function in the point 1 divided by 2 pi and minus 1 divided by 2 pi is equal to pi. So you may be asking yourself why the question is asking this. So if you analyze what you've just found, if you substitute those points in x, you'll have here x squared will be 1 divided by 2 pi squared. That's 1 divided by 4 pi squared. So it will cut out with this 4 pi squared here. So you'll have 1 minus 1, that's 0. And if you substitute here 1 divided by 2 pi, you'll have sine of pi, and that's 0 as well. So you will have 0 divided by 0. That's not determined. So you need to use limit or other methods to define the value of the transformed Fourier function on those points. Okay, so that's why the question is asking for this. And well, there is two main methods of doing it. Here you can go by the definition. So here you use the definition of the Fourier transform. So it's the integral of the function times this exponential. So you can substitute here in your x, because when you're integrating, you're considering that x is a constant. So you can determine this constant by substituting the values plus and minus 1 divided by 2 pi here and do the integration again. This will give you the right answer. This will show that the value is pi. Or you can just pick what you've found. It's basically this. You can just pick this, and you need to calculate the limit when x tends to 1 divided by 2 pi or minus 1 divided by 2 pi. So if you calculate the limit here and reach pi, you also demonstrated what the question is asking for. So I don't know exactly which methods that you learn about limits, so I'll use L'Hopital. So here we're going to calculate the limit when x is tending to 1 divided by 2 pi of the function that we've transformed. So that's equal to limit of x tending to 1 divided by 2 pi. Now let's write again the function 4 pi x sine 2 pi squared x divided by 1 minus 4 pi squared x squared. So basically the concept of L'Hopital is if you're tending your x to a certain value and your numerator is going to 0 and your denominator is going to 0, then you can apply L'Hopital. So what you're gonna do is you're gonna derivate the numerator and divide it by the derivative of the denominator. And then you're gonna do the same limit, but this time you won't have 0 divided by 0. You will have a value, and that's the limit of your, that's the correct value of the limit that you intended to calculate. Okay, so let's derivate the numerator. So the numerator will be the derivative of this, that's 4 pi times sine of 2 pi squared x plus 4 pi x times 2 pi squared times cosine of 2 pi squared x. So what I've done here is I've considered 4 pi x as an f and sine of 2 pi squared x as a g. So if you want to derivate f times g, you're gonna derivate f and multiply by g, and then you're gonna add the derivation of g times f. So I've basically done this. Okay, and now we're gonna derivate the denominator. That's easy. The one is gonna vanish, and here we'll have minus 8 pi squared x. Okay, now we can just substitute the value of 1 divided by 2 pi, and we'll have a value for the limit. So here, if we have 1 divided by 2 pi in this x here, we'll have sine of pi, that's 0. So this whole term here is 0. So let's analyze this part right now. So this one will be 2 pi squared times 1 divided by 2 pi. That's cosine of pi, that's minus 1. So I'll just erase it and put minus 1. This minus 1 will cut out with this negative, so I'll just erase it. I'm erasing minus 1 and I'm erasing the negative sign here. Okay, so right now we have 4 pi x, so I will erase x and put 1 divided by 2 pi. So what we have here right now, this pi will cut out with this pi, this 2 will cut out with this 2. So in the numerator, we'll have 4 pi squared, so 4 pi squared. And here on the denominator, let's substitute x by 1 divided by 2 pi. So the pi will cut out with this square. The 2 will cut out with this 8, we'll have 4, so 4 pi. And then 4 pi squared divided by 4 pi, that's pi. Okay, so we've calculated the limit of the transformed function when x reaches 1 divided by 2 pi. And the logic is the same if you make the x tend to minus 1 divided by 2 pi. Actually, the application of L'Hopital is the same. You're just gonna substitute a different value for x, so minus 1 divided by 2 pi. This sign here will go to 0 as well because sine of minus pi is also 0. And here you won't have a you'll have like minus 4 pi squared divided by minus 4 pi, but you'll reach pi once again. So yeah, in order to save a little bit of time, I'm not doing the calculation again, but it's literally the same. So now we can say that we've finally done with question 2. So now question 3, we need to calculate the value of the integral going from 0 to infinite of u sine pi u divided by 1 minus u squared du. Okay, so the idea here is we're gonna do the inverse transform of Fourier. So, okay, so the formula is f of theta, since we're gonna invert it. So it's like d transforming. So f of theta is equal to the integral, considering the real numbers, of the transformed function. So this f of x here that we've found, times the positive exponential of 2 pi I theta x dx. So that's the formula for the inversion, okay? So let's expand this. We'll have the integral, real numbers. The f of x that we've calculated here is 4 pi x sine of 2 pi squared x divided by 1 minus 4 pi squared x squared times exponential. Okay, so if we look once again at the question here, we can see that he's using u instead of x, and it's kind of easy to see that he did a variable change there. So we're gonna do the same in order to try to make our integral here be closer, be more similar to the one he's asking for. So let's do u equals 2 pi x. Okay, so if we rewrite this, we'll have f of theta equals the integration, the real numbers of, here we have 4 pi x, so we'll have 2 times u, sine of 2 pi squared x, that's pi times u, and we're gonna divide it by 1 minus u squared. Okay, here we have the exponential of 2 pi x I theta, so u I theta, and here we have dx. Okay, so since we have this change of variable, our du will be 2 pi dx, so dx equals du divided by 2 pi. Okay, so let's substitute it here. So since we have dx here, we'll have du divided by 2 pi. Okay, so we just did the variable change, okay? And of course, the real number stays the same, since this variable change won't change the limits of our integrals, since the real numbers is actually the integration between minus infinite and plus infinite. And if we substitute here in x plus infinite, we'll have plus infinite for u. And if we substitute here minus infinite, we'll have minus infinite for u. So these r here won't change. Okay. So you can see that this 2 here can cut out with this 2 here, so I'll just erase it. All right. So what's the final idea? Here we have an equation of f theta, it is equal to this integral. So if we pick a value for theta, this f of theta will become a number because we'll have the value of it. And also we can make this exponential vanishes. And why we want that? Because we want to make the integral that the question is asking for appear, and the integral that the question wants does not have this exponential here. So if we pick theta equals 0, we'll have f of 0, that's cosine of 0, that's 1. And now, when we rewrite our integral, we'll have u times sine of n pi, of pi u, sorry. This exponential will be exponential to the power of 0 since theta is 0, so this is just 1, so we vanish it, okay? Du divided by pi here, and 1 minus u squared. Okay, so that's the integral that we wanted, except for the fact that here we have the real numbers, and the integral that the question is asking for is from 0 to plus infinite. So here is the last trick that we're going to use. We need to analyze that u is an odd function, sine is an odd function. So here we have a product, a multiplication between two odd functions. That's a pair function. And 1 minus u squared, that's pair. So basically we have a pair divided by a pair, that's a pair. In sum, we are integrating a pair function. And if we are integrating a pair function, we can multiply it by 2 and cut the interval in half. So we can have 2 times, here the integration, but we'll cut it in half, u sine of pi u du divided by pi 1 minus u squared. So now it's easy. We just multiply this pi here. So instead of 1, we'll have pi. Instead of 2 here, we'll have divided by 2 in the other side. So that's the final answer. That's the value of the integral that the question was asking for.